You are currently the only person in this conference.
Welcome back to the virtual classroom of Chembase School of Chemistry. Can you hear me? Sound clear? Am I clear to everyone? Okay, great. I hope all of you have done this March 2021. This is the latest paper out. I have advised you to do this as the mock exam just before the examination. And just for your note that this paper is not yet officially out. It's not available online. And also at this point of discussion, neither the marking scheme for this paper has been still out. So the marking scheme is not yet out. So let's discuss. This is a very important paper. And I hope all of you have done this with proper timing. This is a 2-hour paper as usual. To begin with, and all of you should mark your papers and let me know the marks at the end of the lesson. The most common oxidation states of cobalt are +2 and +3. Complete the electronic configurations of the following free ions. Now, cobalt 2+ and cobalt 3+. Now, cobalt has 27 electrons. If you analyze the atomic number, is 27. Atomic number is 27, which means it has 27 electrons. So if I'm to write the configuration of cobalt, so argon, up to argon is about 18 electrons are covered. So you have argon, then you got 3, up to this is 3D, 3S, or 3S and 3P all filled here. So you have 4S2 filled along with the 3D 7. Now this is the configuration of cobalt, not cobalt 2+. This is cobalt. So you remove the electrons. 2+ means you remove the electrons from the outermost. So cobalt is argon and 3D. You first fill the 4s2, come back and fill the 3D level. So remember always the 4s2 has to be in the outer shell because of the repulsion, and the 3D is filled afterwards. So the 2 electrons are removed, that is from the 4s. So therefore it will be 3D7, nothing in the 4s, and 3+ is 3D6. You remove an extra electron than the cobalt 2+. So right, this is the cobalt 2+ and 3+ configuration with respect to argon. So here you have argon 18 electrons, and 18 + 7 is 25. So cobalt 2+ has got 25 electrons, and cobalt 3+ got 24 electrons. Cobalt 2+ and 3+ both form complexes with ethylene diamine tetraacetic acid, which is EDTA4- overall. Use the data from the table to predict what happens, if anything, when separate aqueous solutions of cobalt 3+ and cobalt EDTA complex are left to stand in the air. Now, when you left to stand in air means you're keeping this exposed to oxygen or water, right? Air contains about 20% oxygen and about 1% moisture, right? So let's see what happens. Now, cobalt 3+ equation is this, and oxygen equation is this, right? So we have to consider these 2 equations, right? And cobalt 3+ can't be cobalt 4+. There's no cobalt 4+. It's only 2+ and 3+. So therefore, cobalt 3+ cannot be oxidized to 4+, right? So definitely we know cobalt 3+ will not react with the oxygen, because if cobalt 3+ to react with oxygen, then cobalt 3+ will get oxidized to cobalt 4+. In fact, there's no cobalt 4+ here, right? So cobalt 3+ should get reduced, right? So it has to get reduced to 2+. So therefore, the equation should be cobalt 3+ to 2+ is one equation, and the other equation should be the reverse of this equation. That means it is reacting with what? Water, not with oxygen. Water, O2 plus 4H plus 4 electrons, right? It's reacting with water, not with oxygen, because it cannot react with oxygen. In that case, you can't have 2 reducing equations. You can't add these 2 equations, right? Both are reductions. So one has to be oxidized. So we have to reverse this equation. So Why I reverse it? Because cobalt 3 plus to 2 plus has a greater reduction potential, which is plus 1.82, which is more feasible for reduction. And with respect to this equation, which is less positive, which is more feasible for oxidation. So when I add these two equations, I get the overall equation, right? But we are not supposed to write the overall equation here. But if the question says what happens, predict what happens, so you just predict. But to predict, we need to know what happens, whether the reaction takes place or not. But in this case, the reaction does take place. It produces cobalt 4 plus to water, and the overall reaction, we don't use reversible arrows, 4 cobalt 2 plus, and this is the oxygen, and 4 H plus, right? This is the overall equation. If I am to write the overall E cell value, check whether it will take place or not. This is plus 1.82 and plus 1.23. This is E cell equals E cathode minus E anode. We know the red cat. Reduction occurs at the cathode, so you can say E reduction minus E oxidation as well. So cathode is a one-way reduction occurs, which is first equation. This is a reduction equation, which is plus 1.82 minus 1.23. So you get overall positive reduction potential. Therefore, this is feasible, right? So cobalt 3 plus get reduced to cobalt 2 plus in the presence of water in air. So this particular reaction is feasible. Now the question arises, will water further reduce cobalt 2 plus to cobalt? Can this happen? Let's see. Let's analyze the equation. That's an important question, because we don't know whether it's going to stop at 2 plus. If cobalt 3 plus can reduce to cobalt 2 plus, how do you know whether it's going to stop at 2 plus or it's going to further get reduced? So in that case, you have to consider these two equations. And when you consider these two equations, you know this is not going to happen, because overall cell potential is going to be negative, right? So if I'm to write this as reduction and this side reverse this as oxidation, then minus 0.828 and minus 1.23 overall, we get still a negative value. So cobalt 2 plus is not further reduced to cobalt in the presence of water. So water is not so strong to reduce further up to cobalt. So what happens here? Cobalt 3 plus is reduced to cobalt 2 plus in the presence of water in the air. Overall cell potential is positive. Clear? So you can write this expression and say this is positive because this takes place, but it's not a must to write overall equations here. You can simply calculate the E cell value and say, because it's positive, cobalt 2 plus, cobalt 3 plus is reduced to 2 plus in the presence of water in the atmosphere. Right, so you can check your answer. It should be written as cobalt 3 plus get reduced to cobalt 2 plus, the presence of water in the atmosphere, as the overall cell potential is positive. And it is not further reduced to cobalt. And it is not further reduced to cobalt. Right, the next is aqueous solution of EDTA, cobalt EDTA complex. Now try to understand what is the charge here. It is +3, right? Because cobalt is +3, EDTA is -4, +3 and -4, you get the overall charge of the complex being -1. That means we have to consider this equation, which is cobalt EDTA minus plus E. Then again, I had to write this as reduction, because now see, this is cobalt. In this case, is cobalt is +3. What is cobalt here? -2, right? Minus. This is reduction. This is reduction, right? Because you cannot oxidize, because it says aqueous solutions of cobalt EDTA cobalt 3 plus solution, right? So you can't start from the 4 plus. This is, I mean, you can't start from the 2 plus. So this is 3 plus to 2 plus EDTA 2 minus, and this is plus 0.38. So if I'm to reverse the other equation and say this reduction is possible in the presence of water, then water turning to oxygen plus 4H plus 4 electrons, and then in that case it's plus 1.23. If I'm to analyze the E cell value, E cathode, which is reduction, red cat, minus E anode, cathode is what? The first equation, which is 0.38, and anode is second equation, 1.23. You can get a negative value. You get a negative value for E cell, which is not feasible. So aqueous solution of EDTA minus 1 complex reacting with moisture in air, nothing is going to happen. The reaction, we can say, is not feasible, as the overall E cell value is negative. You can calculate the overall E cell value and show it's negative. So the reaction is not feasible. CO-EDTA minus is not reduced to CO-EDTA 2 minus. It's not reduced to CO-EDTA 2 minus in the presence of water, as the overall E cell is negative. There's 3 marks here. Most probably 2 marks for the previous one and just 1 mark for this one. Why 2 marks for the previous one? I'm not exactly sure to say, because it's still the marking scheme is not out at this point. As far as I am concerned, the 2 marks for the previous one should be for the mentioning of further reduction of CO2 plus to CO is not possible. So just mentioning that, you should get extra mark as to my understanding. And then this is the the third mark, right? Because remember, it cannot react with the oxygen, because cobalt 3 plus cannot be further oxidized to 4 plus. So it has to be always reduction of 3 plus to 2 plus. So therefore, this equation has to be reversed as to the oxidation to take place. I hope that's clear. Any questions there before I move on to the next one? I prefer if you have any questions before I move on to the next question, please let me know. Hydrated cobalt 2 nitrate is a red solid that behaves like hydrated magnesium nitrate. Now, this is important because it says the chemistry of group 2 nitrates. As we know, the chemistry of group 2 nitrates, when we have handled questions like this before in the past papers, when you heat this, first thing to happen is the water of crystallization will be lost, right? And when you further heat, the group 2 nitrates will decompose to give the oxide, nitrogen dioxide, and oxygen gas. So that's the observation for the group 2 nitrate, and it says it's almost same observation, same chemistry for the cobalt 2 nitrate. Describe in detail what you would expect to observe when crystals of cobalt 2 nitrate hexahydrate are heated in a boiling tube gently at first and more strongly. So when you gently heat, what happens? It will lose the water of crystallization. This is the explanation, not the answer, because you can't write for the observations. What you would see, it says, right? Observe what you would see. So you can't say what is given off. So observation would be, upon gentle heating, there will be a liquid condensed on the top part of the boiling tube, this part. This is a solid. The liquid is condensed here because here it's hot and this part is cooler, so the water gets condensed there. This is upon gentle heating. So you can say upon gentle heating, that's 1 mark, liquid get condensed on the neck of the boiling tube. That's 1 mark. You don't say water because it's observation. And then about strong heating, what happens? Like the group 2 nitrates, you get the oxide and the nitrogen dioxide plus oxygen. So upon strong heating, the observation would be a brown gas evolved. You can see a brown gas. And then you also see, you can mention a gas which turns or which relights a glowing splint. So you can either one of the observations you can write or both. You can just say brown gas evolved. That's the obvious observation upon strong heating. And then you can say a gas evolved which relights a glowing splint. Clear? The 2 marks, the 2 observations, general and strong heating. Any questions there? Can you say blue solid formed? If you blue solid formed calcium oxide, we are not sure about the color of the calcium. This cobalt oxide. So you don't need to mention about the cobalt oxide color, right? Because it is, if you are sure of the color, then you can mention, right? It is actually a blue color, sometimes seen as a gray solid, sometimes seen as a blue solid. So it depends, right? Sometimes greenish color, gray. It depends. So it's a little difficult for us to say the color of the cobalt oxide, right? So don't need to comment on the color of the cobalt. But if the group 2 oxides, we know for sure, right? We know for sure group 2 oxide. We know it's a white solid, but in here we have not studied the color of the oxides of the transition metals, right? We never studied those, right? So it can be sometimes seen as a gray or sometimes seen as a bluish green color. I'm not sure about the color anyway. There's a question, because water is also produced, can we give the test for water? No. I don't need to mention the test for water. You can just say, they're just asking for the observation, because they're not asking for to test, because it's just 2 marks, right? If you try to write extra, then I fear that you might not have enough space to write everything, because when you're writing the answer, maybe extra 1 line is fine, but if you try to write a lot more, that means you need to know that your answer is wrong, because sometimes when you write extra, you might lose 1 mark because you don't know, that indicates that you don't know how to present your answer. For example, if I ask a particular question and if you give extra answers for that, including the correct answer, that means you don't know how to answer the question. So they're not telling us to test for water, but it's not necessary to test for water here. You can just say liquid which condenses on the neck of the boiling tube, and you can say a brown gas evolved, and then a gas which turns brown gas evolved is fine. You get 2 marks. And also, if you want to mention about oxygen, you can say gas evolved which relights a glowing splint, because you cannot see oxygen. But in the case of water, you can see it, right? Explain why the thermal stability of group 2 nitrates increases down the group. Now, this particular question we have handled so many times. We'll talk about the ionic radius. Down the group, the ionic radius increases, right? Because size increase, number of shells increase. Then as a result, the charge density. What is charge density of the polarizing power? That is charge over size. When the size increases, the charge density decreases. So down the group, the size of the ion increase. As a result, the charge density decreases. Charge density decreases. The cation will be less able to polarize the nitrate ion. Well, nitrate ion is less polarized. Less polarized. The smaller one, nitrate ion is more polarized like this. But as you go down, polarization is less polarized. This will result in increased ionic character. As a result, the ionic character increases. The thermal stability increases, because when the ionic character increases, the thermal stability will increase. So 2 marks. The ionic radii increases. Charge density decrease. As a result, the cation will be able to less polarize the anion. This results in increased ionic character, and that will cause the thermal stability to increase. You can also talk about distortion of the bond. That's correct. Less distorting the nitrate. Yes, that's correct. So that is 8 marks in total. You're supposed to add the marks now. If you have marked the paper, and on the car page, you can just write out of 8 the total. That's the first question. Anything to clarify further? Question number 2. Iron 2 compounds are generally only stable in neutral, non-oxidizing conditions. It is difficult to determine the lattice energy of iron 2 oxide experimentally. That is why we use the indirect route based on Hess's law. Use the data from the data booklet and the Born-Haber cycle to calculate the lattice energy of FeO in kilojoules per mole. Now, this is they have already drawn the Born-Haber cycle, which makes it very easy for us to answer the question. Remember, let me write the values here. Let me write the values. I need your help with the data booklet so I can save time. So this is the formation, and this is the what is this? Atomization of iron, and this is the atomization, enthalpy of atomization of oxygen. Now, they haven't given the atomization values. So bond energy values are given. Can somebody help me with the values of the bond energy of oxygen? That's right, it's 496 times half. Why times half? I'm getting different answers now. 496, 152, 40, which means I need to take out the data booklet. Can't have 4 different answers, right? Let's check the data booklet and refer to the data booklet and see it says the bond energies here. Let's see. Oxygen double bond energy is 496. I don't know how you got 150 and 248, right? So 496 is the breaking of oxygen double bond, right? Please give me the correct values in future. So that is half of it, because why? Because we are breaking half a mole. That value 496 is for 1 mole. That's for 1 mole. So you're breaking half a mole, 496 into half. So let me write 298. No, this is okay, 248. Fine. So I'm going to write here half because it's easy for you to understand then. This is 496 into half divided by 2. Next is ionization. First ionization of iron. Can someone tell me the answer for that from the data booklet? 762. These are all positive values. Arrows are going up is positive, down is negative, right? And then you got the next one, which is the first electron affinity of oxygen. The value for that, please, 1560. That's the first electron affinity, which is always endothermic. And second, first is always what? Exothermic, right? This is what? This is second. This is not electron affinity. This is second ionization energy of iron. This is 1560. Right. Next comes electron affinity values are given. And now what we should do is, you can see these arrows are all in the same direction, right? Head to tail, head to tail, head to tail. This is head to tail, head to tail, head to tail. So far, if the arrows are arranged in head to tail combination, you can add those arrows together and make it equal to the arrows which are on the opposite side, meaning this one. This is opposite, right? This is tail to tail, head to head. Tail to tail, head to head. So these are all arrows. Head to tail, 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 head to tail. You can add all these, make it equal to this value, right? So plus, that's application of Hess's law. So according to Hess's law, plus 416 plus 496 over 2 plus 672, and keep adding, keep adding. This is 1560. And then you got 141 minus 141. I hope we don't need to multiply anything there. Nothing. And if there's 2 moles, you need to multiply by 2. But in this case, there's no 2 moles, all 1 mole. So it's then plus 798. Plus 798. Then plus lattice energy equals the value of formation, which is minus 272. Can someone tell me the value for lattice energy, please? Is that correct? Minus 3,915 kilojoules per mole. Right? I hope all of you got it right. Remember, lattice energy, if you have, say, 2 moles here, you will multiply by 2 to refer to the definition of each and every enthalpy change. Definition will help you to identify whether you need to multiply the atomization by 2 or not. Most naturally occurring samples of iron 2 oxide are found as mineral wustite. Sorry, wustite, yes. Looks like it's like a German term. Wustite has a formula of Fe20OX. It contains both Fe2 plus and Fe3 plus ions. 90% of the iron is present as Fe2 plus and 10% is Fe3 plus. Deduce the value for X. This is Fe2 plus is 90%. Fe3 plus is just 10%. Now, look here. Now, Fe forms what? Fe2 plus forms FeO, right? Fe2 plus forms FeO. 2 plus and 2 minus cancels. Fe3 plus forms FeO3, Fe2O3, because the valence is cancelled. So these two together is what you get as Fe20OX. So we need to find now, out of Fe20, 90% is 2 plus. Right? We need to find how much is 90 out of 20. 90% is how much out of 20? Let's see, out of 20, 90% is 2 plus. Let's see how much is 2 plus, 18. That's right. So Fe2 plus is 18 out of 20. It means obviously the balance will be 2, right? Fe3 plus has to be 2. So if its balance is 10%, sorry, 20, 10% out of 20. We know it's 2, right? So Fe2 plus is 2 atoms. So out of 20, Fe2 plus is 18 and Fe3 plus is 2. If Fe2 plus is 18, that means oxygen also will be 18 here because it's 1:1. But Fe3 plus is 2, oxygen will be what? 3, right? Because 2:3. Ratio is 2:3. Right? It's quite a straightforward question, right? If Fe18, Fe2 plus is 18, oxygen also has to be 18 because 2 plus and 2 minus is 1:1 proportion, right? Here, if it is 3 plus is 2, O has to be 3. So how many oxygens total? 18 plus 3, 21, right? So X is 21. So it's Fe20O21. Got it? That's quite interesting question, but it's all to do with mass. Got it? State and explain how the lattice energy of iron 2 oxide compares with the lattice energy of the calcium oxide. No, here the lattice energy depends on 2 factors, as we know. Lattice energy is directly proportional to the charge and is inversely proportional of the ionic radius. Before I move on, there's a question how it's 18. It says 90% of 2 plus is 90% is 2 plus. So out of 20, 90% is 2 plus. 20, 90% is 2 plus. What is that then? 90% of 20 is what? 18. So 2 plus is 18 out of 20. If 2 plus is 18, 3 plus is 2, right? Because total is 20. Got it? Chem 8, is it clear? Now look, no need to complicate this with any other calculations. Only this you need to work out. If look at Chem 22, look at this. If Fe is 18, how many oxygens should be there? 18 oxygens, because 1:1. Got it? 22. Chem 22, did you get the explanation? If Fe 18, oxygen should be 18 because 1:1, right? Got it? So this is 18 oxygens here. Other one is Fe2O3. So Fe is 2. then oxygen should be 3, right? 2 ions combining 3 oxygens. Got it? So you have here Fe2 18, Fe3 plus 2, so 18 plus 2 is 20. O here 18, and this is 3. 18 plus 3 is 21. 18 plus 3 is 21. That's the answer. Okay. So here we cannot talk anything about the charges, because plus 2, minus 2, plus 2, minus 2. Charge explanation is out. We talk about the sum of the ionic radii. You can check the data booklet and get the ionic radii of Fe2 plus and calcium 2 plus. It is not that you have to write the values. You don't need to quote the values, because in this question it does not say with the help of the data booklet. Whenever it says in the question with the help of the data booklet, then you have to quote the value from the data booklet. But you don't need to quote in this case. And we know calcium and iron. Calcium is huge compared to iron because it's the same period. Across the period from left to right, the atomic radius decreases. Even if you don't look at the data booklet, still you know iron is small in size compared to calcium, because across the period from left to right, the atomic radius is going to decrease because the nuclear attraction is going to increase. Number of shells are constant. Shielding effect is constant. Electrons will be strongly attracted towards the nucleus when you go from calcium to iron. Got it? So iron is small in size compared to calcium, right? So the iron 2 oxide will have a smaller sum of the ionic radii. Therefore, the lattice energy of the iron 2 oxide will be much greater than the lattice energy of the calcium oxide. So mention here, Fe2 plus has a small ionic radii compared to calcium 2 plus. As lattice energy is inversely proportional, to the sum of the ionic radii, as lattice energy is inversely proportional to the sum of the ionic radii, lattice energy of FeO will be much greater. Lattice energy of FeO will be much greater compared to CaO, calcium oxide. Heating iron 2 oxide results in the formation of the mixed oxide, which is Fe3O4. The equation is given. Each formula unit of Fe3O4 contains Fe2 plus, one of the Fe2 plus. You have one Fe2. That's why I said it's a mixed oxide. One of the Fe2 plus and 2 of Fe3 plus. It's a mixed oxide of Fe2 oxide, iron 2 oxide, and Fe2O3, 2 of this. So when you mix together, right, you get the mixed oxide. Anyway, let's look at the question. Show how reaction 1 can be described as disproportionation. You can clearly notice the simultaneous increase and decrease in the oxidation state. Iron in iron 2 oxide is +2. Iron in Fe is 0. So this is decrease in oxidation state, which is reduction. And let's analyze the oxidation number of iron in Fe3O4. I take iron as X, so it's 3X here. 3 iron, I take each iron as X, 3X minus 8 equals 0. Why minus 8? Because each oxygen is -2. -2 times 4 is -8. So 3X equals +8. X is 8 divided by 3. So it's 2.6. This is 2.6. So here you can notice oxidation number has increased to 2.6. So simultaneous increase and decrease in the oxidation number. That's why it is disproportionation. You can say iron has decreased and increased its oxidation state simultaneously. iron has increased and decreased its oxidation state simultaneously. There's a question in that complex. Yes, this complex. One is +2 and other one is +3. Yes, +2 and +3. You're right. The question says that. You're correct. Yes, you're right. So we need to calculate. You're right. Shouldn't we take that? Y 2.6? Yes, you can. I just took the overall, the state of iron, overall state of iron as compared to she's correct, right? That is +3. You can directly take that way also because question says so. So +2 directly increase to +3. That's a good approach. Good approach. Yes. No need to calculate and waste time. What I did was I just found the state of overall iron. Even if you take the state of overall iron, still you can show as increase in oxidation state. But as Chem22, that is not necessary because you know it's anyway increasing to +3. And the question carries only 1 mark. And it doesn't say using oxidation numbers. So you have to simply say iron has increased and decreased its oxidation state. So it's disproportionation simultaneously. Iron has increased and decreased its oxidation state simultaneously. Okay. The mixed oxide can be electrolyzed using inert electrodes to form iron. Write the half equation for the reaction that occurs at the anode during the electrolysis of Fe3O4. Anode attracts the anion, right? So the anion here, there are 2 cations. There is 1 Fe2 plus and 2 Fe3 plus ions, right? The anion is only oxygen. So oxygen will, that is O2 minus this gives oxygen, right? So O2 minus 4 electrons gives oxygen. You can also add the 4 electrons on the other side. As for Chem 3, your question, oxidation numbers to show is not necessary. Just 1 mark. With 2 marks, yes, you can show. Calculate the maximum mass of iron metal formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 amperes. We need to first of all work out the charge which we send, because as to the Faraday's first law of electrolysis, the amount of solid deposited during electrolysis is proportional to the quantity of electrical charge. That's the Faraday's first law of electrolysis. So the current I is 50. Time is how many minutes? 6 hours. So it means 6 into 60 into 60, right? In minutes, because 6 hours to minutes you multiply by 60. To convert minutes to seconds, we have to multiply by 60 again, because time has to be in seconds. So you get the answer. Thanks for that. 1.08 into the power 6 coulombs. And now we got the 2 equations. Fe2 plus 2 electrons, Fe2 plus turns to Fe this way. And you got 2 Fe3 plus 6 electrons turning to Fe. Because there are, the question says there are 1 Fe2 plus and 2 Fe3 plus, right? So this is how overall what happens. So overall equation, you get how many electrons here? 8 moles of electrons for 3 Fe. 3 moles of Fe to deposit, we need 8 moles of electrons. We know the charge of 1 mole of electron, right? Charge of 1 mole of electron is 96,500 coulombs times 8. You get the overall charge, which is required to deposit 3 moles of iron. 1 mole of iron is 55.8. And you can work out the mass of 3 moles of iron, which is deposited by 8 moles of electron. So 1 mole of electron is 96,500 coulombs. That times 8, the total charge, which is required to deposit 3 moles of iron, where 1 mole of iron is 55.8. 3 moles will be 3 times of that. So this amount of coulombs gives that much of iron. We don't have this amount of coulombs. We got 1.08 into the power 6 coulombs gives how much of iron? This divided by 96,500 times 8 multiplied by 1.08 into the power 6. What's the final answer, please? In grams, you get the answer in grams. (26.02). Such a small mass for 3 hours, also 6 hours. Let's check again. I have a doubt about that because it's 6 hours, right? We'll see. 1.08. Maybe it can be correct. We'll see. Anyway, divided by 96,500. Please don't do any mistake in multiplication, addition, division. Can't afford to lose a mark because of you don't know how to add and multiply. Can't afford to do that at this stage. That's correct. 234.2 grams. Clear? So it's again, you find the coulombs, construct the overall equation, get the overall moles of electrons and the overall moles of iron deposited. Then you can simply calculate from this relationship. Please, you can get 3 marks, 1 mark for the Q equals IT, 1 mark for the analyzing the 2 moles of electrons and 3 moles of iron, and 1 mark for the final answer. Okay. Lithium iron phosphate can be used in lithium ion rechargeable batteries. You know, lithium ion rechargeable batteries are very light and you can recharge again and again, and you can use for a long period of time, usually in mobile phones and portable devices. Even these button cells are lithium ion. When the cell is charging, lithium reacts with the graphite electrode to form LiC6. When the cell is discharging, the half equations for the 2 processes that occur are as follows. The cathode and the anode reactions for discharging is given here. Right. State one possible advantage of developing cells such as lithium-ion rechargeable batteries. There are so many advantages. You can say it's lightweight, it consumes less space, right? It's lightweight, consumes less space. You can also say, don't mention about rechargeable because it's already mentioned as rechargeable here. So don't say it's rechargeable again. I doubt. Portable also is not a good option because most of the cells are portable. Even the huge, nickel cadmium cells itself is portable, right? But it's heavy. But say lighter, takes less space. Lighter, less space. Those are better answers. I'm not sure because we don't have the marking scheme out yet at this point, so we don't know whether the given marks for is reusable. Yes, that's a good point. It's reusable. You can use again and again and again. We can recharge and use reusable. That is a good point. But don't say rechargeable because it's already given the word rechargeable. So don't say it's rechargeable. No. Cost of making new batteries reduced. Not cost of making new batteries reduced. Cost of purchasing new batteries always is reduced, right? Manufacturing cost won't reduce just because you have lithium ion, but the person who is using lithium ion, you don't need to buy all these batteries. It's one time, then you can use it for so many times you can charge. Anyway, there are so many options. So better option, I would say, the lightweight and consumes less space. That will be a better option, and it's reusable is also fine. Should be okay. Use the cathode half equation to determine the change, if any, in the oxidation states of lithium and iron at the cathode during discharge. This is the equation for discharging anyway, right? So oxidation state of lithium, discharging from 2. This is lithium. This is anode and cathode. This cathode, right? Cathode. So lithium is for +1 here. What about this one? This is quite strange. We have to be a little careful here. Lithium can't be 0 right now. It takes electron, but this electron lithium cannot take. You know why? If lithium takes the electron, lithium turns out to be neutral. Then how come the neutral lithium attracts the FePO4? So this is quite tricky. We have to be careful here. So the electron is not attracted by the lithium, definitely, because if lithium attracts this electron, lithium will turn out to be neutral. Then how come two neutral compounds, FePO4 is also neutral, right? So how come two neutral compounds bound together? So definitely the electron, therefore, should go into this complex. This should be negative. Therefore, lithium will remain positive. So lithium is positive. This whole thing should be negative. Lithium does not change its oxidation state. So iron, we know, is +3 here. This iron, sorry, it's +3. Yes, +3 because iron 3 phosphate. And here is +2. How is +2? Because FePO4 -1. PO4 is -3. No, phosphate is -3. So iron has to be +2. +2 and -3 is -1. So electron is taken by whom? Electron is taken by the Fe3+, and it has turned out to be Fe2+. Clear? Write the equation for the overall reaction that occurs when the cell is discharging. All what you have to do is to add the two equations simply. And when you're adding, make sure the electrons are equal. Therefore, should get cancelled. But here, you know the electrons are already equal. So you can just simply cancel the electrons. You can cancel the lithium and then add Li(C6), FePO4, LiFePO4, and 6 carbon. This is the overall. Simply add the two equations. In case if the electrons are not equal, we need to multiply by a common figure to equalize the electrons. Sorry, this is page 7 here. Clear? So you can add the marks out of 13. This is we're discussing question 2 still. Still question 2, almost an hour gone. Right, anyway. Right, please write the total marks. Question number 3. Iodates are compounds that contain IO3- iron. Iodine here is +5, right? This is iodate 5 iron. Iodine is +5. Oxygen is -2 times 3 is -6. +5 and -6 is -1. Explain with reference to the qualitative model of electron pair repulsion why IO3- anion has a pyramidal shape. Now remember, iodine, if you know the Lewis theory, it's very easy. Iodine has 7 electrons and oxygen has got, in the valence shell, oxygen has got 6 electrons. 3 oxygen, 6 times 3 is 18. So this has 25 electrons in the valence shell, and then in the outermost shell, there's extra negative charge, so I need to add an electron. So it's 26 electrons in the outermost shell. And if I divide this by 2, I got 13 electron pairs. Let's see how many electron pairs are shown here. That means the outermost shell should have 13 electron pairs. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This negative charge is 12. 11, 12, 2 electrons there, right? So I have shown here, in the structure is already 12 electron pairs are shown. Out of 13, each bond, remember, is a pair of electrons. So this is 2 dots. So how many electrons are shown here in the outermost shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 13 electrons. So that means there is a lone pair on the iodine. That means there is a lone pair on the iodine. I advise you to go through the AS Lewis theory on the Saltipack 3 chemical bonding. There's a lone pair. So what happens? Just like ammonia. It's just like ammonia, right? The lone pair repel the 3 bond pairs, resulting in pyramidal shape. That is the explanation for ammonia, right? The same explanation here. So we can mention the iodine has a lone pair. The central atom iodine has a lone pair. Which repels the 3 bond pairs. Which repels the 3 bond pairs. Resulting in pyramidal shape. This reaction of iodine and hot aqueous sodium hydroxide, we know it's a disproportionation reaction. Is similar to that of chlorine with hot aqueous sodium hydroxide. It gives NaI, NaIO3, and H2O. If you remember how to balance this, you can balance this using the oxidation number method. 0, -1, +5. Here the change is 5, change is 1. Equalize the change, you multiply this by 5, multiply this by 1. No, anyway, this is, yeah, that method you can, that's not very successful. It's not a redox reaction, it's a disproportionation reaction. So anyway, we can, if you remember the balancing of this, it's balanced this way. I think it should be balanced now. So you multiply this by 5, that means, yes, you're correct, even oxidation numbers can be used, right? This is 5, difference is 5. So the difference is 1. So I multiply this by 5. Multiply this by 5, that means I don't multiply iodine by 5 here, but NaI can be multiplied by 5. Iodine, there's already a iodine over here, so I can make it 3 because it's I2, right? I can't make it 5 because 5 times 2 will be 10, right? So that way we can get an idea that it has to be 5 NaI here. So that's how we get the 5 NaI. I hope that's clear. The decomposition of hydrogen peroxide is catalyzed by acidified iodate 5 ions. You know, hydrogen peroxide is decomposed to give water and oxygen, right? We did the experiment with manganese dioxide catalyst, but here the catalyst is IO3 minus. Most probably this has to be a homogeneous catalyst because the IO3 minus and the hydrogen peroxide the same physical state. H2O2 reduces IO3 minus as shown. That means if IO3 minus is a catalyst, and if the catalyst is reduced in the first step, the catalyst should be oxidized in another step. Therefore, it should be reproduced again at the end. Be reproduced at the end again. This reaction, because remember, overall equation should not have IO3 minus because it's a catalyst. So if one of the steps, if it is reduced, on the step it should be oxidized. You can see an equation here. A reduction of IO3 minus to I2 is given. Of course, opposite of this will be the oxidation, reverse of this. Use the data to show that the separate reactions of H2O2 and IO3, H2O2 with IO3, this reaction already is shown, and with iodine are both feasible under standard conditions. In your answer, give the equation for the reaction of H2O2 with I2. So let's first of all show that this is feasible, right? So for the first reaction, for H2O2 with IO3 minus, no need to construct the equation for that because it's already constructed. We notice, let's find the E cell value for that. E cell minus E cathode minus E anode. Red cat reduction occurs at the cathode, so is E reduction minus E oxidation. So what is reduced, what is oxidized here? So here you can notice H2O2 turns to H2O, or H2O2. Now you have to take this as the equation, right? This is one equation. This is reduction. What is reduction? IO3 minus reduced to iodine. So that is the cathode. That is definitely the cathode. So it's plus 1.19. What is the anode equation? This is not the anode equation. H2O2 giving H2O is not the anode equation. Because if that is the anode equation, from where this oxygen came? Anode equation is this. H2O2 breaks down to give oxygen. So you reverse this equation and then add to get the overall. So anode is what? Minus 0.68. This equation cannot be the anode because you can't add these two equations together, right? Because these two are both reductions. How can you add two reductions? You can't do, right? So from that we know, and even if you add these two together, you won't get this this oxygen. So you have to reverse this equation. This is the equation. So overall, 1.19 minus 0.68 is plus 0.51. So from that we know the first equation is feasible. Yeah, for feasible, right? And second part, this is the first part of the question. I hope you will get about 1 mark for this. Right, let's see how many marks given. 3 marks. The other, it says to construct the equation for the hydrogen iodide with iodine. Sorry, hydrogen peroxide with iodine. So hydrogen peroxide plus 2H plus 2 electrons giving 2 water. That is 1.77 and half I2, 3 water giving IO3 minus 6H plus and 5 electrons. This is plus 1.19. Multiply the first equation by 5, second equation by 2 to make it 10 electrons. And you construct the overall equation. 5 H2O2, get I2, just I2. And then you got here 2H plus, 2 IO3 minus, and 4 water. Now, why it's 4 water? Because you can notice here you have 10 water on the product side. Reactant side, you have 6 water. So left side, 10 water. Sorry, right side, 10 water. Left side, 6 water. So overall, I can bring the 6 to the right side and make it water. As for the H plus, you have on the right side, you got 12H plus. Left side, 10H plus. Overall is 2H plus. So E cell is cathode. This is a cathode minus anode. You still get a positive value, so it's feasible. It's positive value 1.77 minus 1.19. Well, it's plus 0.58 volts, so it's feasible. Okay, this is the answer for this. Say feasible. Overall reaction. I had to add these two equations, and I hope it's clear. This equation, I need to add to this equation. Let me write the two equations. The first is H2O2 I2. The overall equation is to cancel all the catalysts. 4 water, and the first equation 2H plus 2IO3 minus 5H2O2 I2 6H2O 5O2. Got it right? 6512. Yes, that's correct. And I add the two equations, see what happens. IO3 is gone. 2H plus is gone. Iodine is gone. That's all. You get 10 H2O2, 5 O2, 10 H2O. 4 plus 6 is 10. So that's the overall equation. There's no catalyst in the overall. Got it? Any questions there? Right, so let's continue the next one. Right, so this is still we are in page 10. It's surprising this is quite a really long paper, 28 pages anyway. February, March paper, maybe it's long. A student collects some data for the reaction of hydrogen peroxide, acidified iodate as shown in the table. To find the order with respect to each reactor. Now here you can do the calculation method, or you can use the calculus method or the explanation in words. So to find the order with respect to hydrogen peroxide, you have to keep the other factors constant and change the hydrogen peroxide. Can you notice experiment 3 and 4? When you consider experiment 3 and 4, you're keeping this constant, and you're increasing the concentration of hydrogen peroxide by 1.5 times. The rate is increased by 1.5 times, which means order with respect to hydrogen peroxide is first order. It's very convenient for us to write in words because the space issue, right? Calculation also is accepted, but if you can calculate in this given space, fine. So you have to write here when experiment 3 and 4 are considered. Experiment 3 and 4 are considered. Increase in the concentration of hydrogen peroxide by 1.5 times. Increase in the concentration of hydrogen peroxide by 1.5 times. Keeping IO3 minus NH plus concentrations constant. Has increased the rate by 1.5 times. Therefore, the order with respect to H2O2 is first order. Next is order with respect to IO3 minus. Let's look at this. IO3 minus. We have to consider which two? Yes, since we got the order with respect to hydrogen peroxide, no, we can't use 2 and 3 because 2 and 3, we don't know the order with respect to H plus, right? So here H plus is changing. We don't know what's the situation of H plus, but we can take 1 and 3. That's right, because already we know the order with respect to hydrogen peroxide, right? Right. So 1 and 3 can be considered. Why? Because 1 and 3, you are doubling the concentration of HiO2, keeping H plus constant, And simultaneously, you double the concentration of H2O2 as well. See what has happened to the rate. Rate is what has happened to the rate. Let's check again. 5.88 divided by 1.47. Rate is increased by 4 times. Increased by 4 times. Right? That means now order with respect to hydrogen IO3 minus is first order, not second order. You know why? Because we are doubling the hydrogen peroxide and doubling the IO3 minus. Rate is increased by 4 times. All these 4 times, 2 is due to the hydrogen peroxide. 2 is due to the hydrogen peroxide. So if the rate, when you double the concentration of IO3 minus and double the concentration of H2O2, if the rate is doubled, suppose if the rate is doubled, then the order with respect to IO3 minus is 0th order, because doubling of the rate is due to the doubling of the concentration of hydrogen peroxide. But here, doubling of hydrogen peroxide and doubling of IO3 minus has increased the rate by a factor 4 times. Out of 4 times, 2 times is due to the hydrogen peroxide. So the balance 2 times is due to the IO3 minus. So it is first order with respect to IO3 minus. You can also do the calculation method. You can say, when you specifically mention which experiment we are referring to, that's very important when you're writing the words. Right? Yep. So check your answers when experiment 1 and 3 are considered. Doubling the concentration of hydrogen peroxide. Doubling the concentration of hydrogen peroxide. And doubling the concentration of IO3 minus. Has increased the rate by 4 times. As the order with respect to H2O2 is first order. As the order with respect to H2O2 is first order. Rate is doubled with respect to H2O2. And doubled with respect to IO3 minus. Therefore, the order with respect to IO3 minus is first order. Continue 2, there's a question. I consider 2 and 3 got the same answer. I'm surprised how you got the same answer, because we don't know the order with respect to H plus 2. Because you're making 2 changes, right? You cannot consider 2 and 3 because you're making 2 changes. How do you know the effect of H plus then? We don't know. How do you know it's 0th order? Right? If it's 0th order, then fine. What if the order of hydrogen peroxide was second order? How would the rate be affected? If it is second order, that's a good question. That's a good question. If it is second order, then the order with respect to IO3 minus will be 0th. Because you know why? If this is second order, doubling the concentration should increase the rate by 4 times, right? If it is second order, right? Doubling the concentration will increase the rate by 4 times. That means Doubling of concentration of IO3 minus has no effect on the rate because it has increased only by 4 times. If this has effect on rate, it will increase more than 4 times. Got it? In that case, it will be 0th order. Got it, Chem 3? So that's a good question because you might have that situation to handle next, right? Never know. Okay. Then comes the H plus. H plus. So we can take which two equations? 1 and 2? Yes, 1 and 2 is easier. Yes, 1 and 2. You're doubling the concentration. This is constant. And you're doubling H2O2. The rate is simply doubled. Doubling of the rate is equal to the doubling of the concentration of H2O2. Therefore, H plus is 0th order. Right? When experiment 1 and 2, doubling the concentration of hydrogen peroxide, keeping IO3 minus constant, and doubling the concentration of H plus has doubled the rate. So this doubling of the rate is due to the doubling of the concentration of H2O2 as its first order. Therefore, the order with respect to H plus is 0th. So it means the rate equation, H plus is not there. H plus is a catalyst. Sorry, it's not the catalyst. It's not a catalyst. Catalyst will have order, right? IO3 is a catalyst. H plus is 0th order. IO3 cannot be 0th order because that's the catalyst. Catalyst will always have order to take part in the slow step. This is the rate equation. Next, I'm not going to do this one because you have to simply substitute any set of values from experiment 1, 2, 3, or 4 to this equation. You know the rate, you know the concentrations. You can find the value for rate constant and the unit can be derived accordingly. You can do that, right? What's the value? Rate is moles per decimeter cube per second. And this is moles per decimeter cube, moles per decimeter cube. So moles per decimeter cube times moles per decimeter cube. So 1 mole per decimeter cube can be cancelled. So unit will be per mole dm cube per second. That's the unit. As for value, you substitute and get the answer. As for Chem 8, is 4.2 10 to the power minus 3. Right? That's the value. More per mole dm cube per second. Per mole dm cube per second. Clear? PbIO3 twice is only sparingly soluble, partially soluble. It has a KSP. As for equation, this will ionize partially to give Pb2 plus and 2IO3 minus. So KSP is Pb2 plus concentration times IO3 minus twice. This is X, this is 2X concentration. Solubility of this is again straightforward. KSP, Pb I take as X. Therefore, if I say let Pb2 plus be X, IO3 minus is 2X, so it's 2X squared. 2X squared. So you have KSP value given, which is 3.69 to the power minus 13. This is 4x cube. So divide the answer by 4 and take the cube root of it. You get the x. Cube root of this. Can someone help me, please, with the answer? I don't want to waste time here. What's the answer here? It's 5.4. I hope this is correct. 4.5 to 10 to the power minus 15. Is it correct? Sorry, 10 to the power minus 5. Okay, fine. Ammonium iodate is an unstable compound that is readily decomposes when warmed. The decomposition of decomposition reaction is shown. Fine. Use the data in the table to calculate the entropy change for this reaction. Entropy change for this reaction. Entropy is a system. Is total the number of moles of entropy of the products minus total the number of moles of entropy of the reactants. The product's entropy is you have to multiply by the moles. Nitrogen 192 divided by 2, oxygen 205 divided by 2, iodine 261 divided by 2, water 70 multiplied by 2. This is the entropy of the products. This answer here. Reactant is just 1. What is the answer here, please? Products entropy. Minus reactant is just 42. Can someone help me with this calculation? Just get me the answer. I don't want to waste time because since you have done it, just get me the answer because I tried to calculate this. I take about, you waste few seconds. Products entropy. Yeah. 469, all positive, correct? Two answers again. Then the final is what? 469 minus 42 is 427 is the final, which is plus 427 joules per Kelvin per mole is the system entropy. Got it? This reaction is feasible at all temperatures. All temperatures. Explain why using the data of F and your answer to F1. Data F and answer to F1. Using this data, you can show this in two ways. One is that you can say, because this is exothermic, surrounding entropy is positive. Because negative is positive. As the reaction is exothermic, surrounding entropy is positive. System is also positive, right? When both system and surrounding is positive, total entropy is positive. So it's feasible at all temperatures, right? That's one approach. You can say, as it says to use F, that means that you use this value, use the sign. As the reaction is exothermic, the surrounding entropy is positive. As both system and surrounding entropies are positive, total entropy will be positive, therefore it's feasible. Right? Or else you can use a Gibbs free energy equation. I repeat again, as the reaction is exo, surrounding entropy is positive. Both system and surrounding is positive, therefore total entropy will be positive. This is one approach. Second approach, you can use the Gibbs free energy. Right? Gibbs free energy. Look here. This is negative. Right? Entropy, this is positive. Positive, negative, this is also negative. Gibbs free energy is negative. If the Gibbs free energy is negative, reaction is feasible at any temperature. Both are correct. Okay? Got it? So you can use Gibbs free energy to explain, or I can say total entropy to explain. That's the question number 3 for 1.5 hours. Anyway, it's okay. The 18 marks, you can add the total. We'll take a short brain break of 5 minutes, and we'll continue the rest after the break. Right, let's continue. I hope everyone is back. This question 4, the transition elements are able to form stable complexes with a wide range of molecules and ions. State the meaning of the transition element. It means an element which has at least one ion with a partially filled d orbital. Element which has at least one ion with a partially filled d orbital. The d orbitals in isolated transition metal ion are degenerate in a complex. In complexes, the d orbitals occupy 2 energy levels. Yes, because octahedral complex, they split in a different way to tetrahedral complex. Octahedral complex splitting pattern will be such that there will be 3 in the lower level and 2 will be in the higher level, right? And tetrahedral complex, 2 will be in the lower and 3 will be in the higher level, right? Now, if you ask me what are these 3 and 2, it's like this. The similar ones always be next to each other. Now this is dxy, dxz, dyz. This is dx squared, dy squared, right? And dz squared. They are similar, right? These are on z squared means they are on the axis, z axis. Dx squared, y squared means they are on the x and y axis. This is how the octahedral complex splits. Explanation is based on crystal field theory. And then tetrahedral complex, this is dx squared, y squared, and dz squared, dxy, dyz, dxz, right? This is how tetrahedral complex splits. So what is in between the axis is what goes to a high level in tetrahedral, and what is on the axis is what goes to a high level in the ligand comes to attack with the lone pair. What's on the axis goes to a high level because lone pair on the ligand repels the dx squared, y squared, and dz squared axis to a high level. Sketch the shapes of 2 d orbitals. 1 d orbital from a lower level in octahedral complex, 1 d orbital higher level in the octahedral complex. Octahedral complex lower level should be anything between x and y orbitals or between y and z. So it should not be on the axis. It has to be in between the axis like this. It should be in between the axis. This is d x y, between the x and the y axis. Draw it properly again. Between the x and y axis. High energy is you can draw on the axis, dx squared, y squared, or you can even draw this. So d is z squared with a ring in the middle, dumbbell with a ring in the middle. So what's in between is xy, yz, xz. What's on the axis is x squared, y squared, or the z squared. Dx squared, y squared is 1. This is x squared, y squared, and this is d z squared. Got it? EDDS 4- and EDTA 4- are polydentate ligands that form octahedral complexes with Fe3+ ferric. The formula of the complexes are this is given, that means this is 3+, this is 3+, yes, 3+ and 4- -1, both are 3+, iron is 3+ in both. On the diagram of EDDS 4- circle each atom that forms a bond with Fe3. But this is a hexadentate ligand, meaning a polydentate ligand. Let me draw. It says draw each atom, circle each atom that forms a bond. Atom, not the group. Not the group. What's the charge of EDDS? The charge is given 4 minus. Right? Circle each atom. So don't circle like this, the groups. Circle each atom. This oxygen, this oxygen, and this oxygen, and this oxygen, and this nitrogen, and this nitrogen. Like EDTA, remember? The lone pair, nitrogen has lone pairs. It forms dative bonds. It's a hexadentate ligand, meaning a polydentate ligand. 6 dative bonds are formed. This is red and this is yellow. Explain why two complexes have different colors. Because if the ligands differ, the extent to which the DD splitting occurs will differ. That is why they absorb different energies for the DD transition. As a result, different complementary colors are seen. Remember, like oxidation state, different oxidation state results in different levels of the DD splitting. That means DD splitting occurs to different extent. Likewise, different ligands matters in the DD splitting because some are strong ligands, some are weak ligands. So when the ligands differ, the extent to which the DD splitting occurs also differs. Right? So don't talk about anything else. Talk about the other factors. When the oxidation now ligand change, you just talk about the extent of the DD splitting. That means the distance between the lower D and the high D difference will be different. Right? You can say different complexes, or you can say different ligands. Different ligands causes the D different extent. I'm sorry, I got disconnected. Is it clear now? Can you hear me now? So I got disconnected. Sound clear? Okay, there's a question from Chem 3. How do we mention when the transition metal ion has two different oxidation numbers? Yes, same explanation. When the oxidation number differs, the extent to which the DD splitting occurs. And I say extent, what I mean by extent is the energy gap between the lower D and the higher D. That differs when the oxidation state differs. And that differs when the ligand differs. So different ligands causes the DD splitting to occur to different extent. Like different oxidation number causes DD splitting to occur to different extent, right? Clear? Okay, so here we can, I'll repeat the answer again because it got disconnected. Because there are two different ligands. These two different ligands causes the DD splitting off to occur to different extent. You can see the two different ligands causes the DD splitting to occur to different extent. As a result, the energy absorbed the DD transition for the DD transition to occur, therefore the energy absorbed for the DD transition to occur is different. As a result, different absorbers is different. Therefore, different complementary colors are seen. As a result, different complementary colors are seen. Yes, the last lines, I don't know what I said. I'll read the whole thing again. Sometimes words will be here and there different. I'm not reading from a note, so you can say, first of all, different ligand causes the DD transition to occur to different extent. Therefore, energy absorbed for the lower D electron to go to the high level is different. Energy absorbed for the DD transition is different. Hence, different complementary colors are seen. Different complementary colors are seen. When EDDS4- is added to Fa3+, the following reaction occurs. Say the type of reaction that occurs. This is a ligand exchange reaction. Water ligand is ligand substitution or ligand exchange is correct. Water ligand is exchanged by EDDS ligand. Case tab for this reaction, we don't case tab, we don't include water. So case tab for this concentration of FeEDDS minus sign should be inside the bracket. What comes outside the bracket is a stoichiometry. FeH2O6 3+ is inside the bracket. EDDS4- inside the bracket, and water liquid state is not included in the case tab. The table valid case tab for both complexes. Predict which of EDDS and ETA complexes are more stable. Explain your answer with reference to case tab. Higher the case tab, greater the stability. You can see the EDTA complex has a greater case tab. When the case tab is greater, it will be greater. And when the case is greater, stability will be greater. The case tab is greater, so which is more stable. EDTA is more stable because it has a greater K-stab value. When excess of EDTA is added to EDDS, the following equilibrium is established. Calculate the equilibrium constant Kc for equilibrium using K-stab values given in the table C4. If I'm to write the Kc for this, then I need to take the Fe EDTA minus times EDDS 4 minus over Fe EDDS minus EDTA 4 minus. This is the Kc expression, right? So now here the EDTA complex is more stable, right? That means this reaction favors the forward, which means your Kc should be a positive value, not point value, a positive value, right? Because it favors forward. So therefore, to get a positive value from this ratio, you have to divide this over that. That means K-stab for EDTA, K-stab for EDTA should be divided by K-stab for EDDS, right? Why? How did I decide on this directly? Because we know the Kc has to be a positive value. I mean, not a decimal answer, because whole number or a decimal answer, because EDTA complex is more stable. That means reaction favors the forward. So therefore, we know directly is K-stab EDTA over this value, K-stab EDDS. Or else we can write separately the K-stab equations. We wrote the K-stab for EDDS, right? And likewise, you write the K-stab for EDTA. This is K-stab EDDS. So you can see this value here. This is there, right? EDDS. You can see here. This is K-stab for EDDS. Already we have written. This is K-stab for EDDS. So therefore, this has to be the K-stab for EDTA. So EDTA K-stab over EDTA, EDDS K-stab, right? So that is, this is already given, 1 upon K-stab for EDTA. So that's another way to do it. There are two ways, right? But whatever the method is, answer is same. 10 to the power 4. That is, you divide EDTA K-stab with EDDS K-stab. Okay, got it. That's question 11. Total 11 marks. Please mark the answers. Fine. So the next question: carboplatin and satraplatin are used in the anti-cancer drug instead of cisplatin. Okay. Describe the action of cisplatin as an anti-cancer drug. Now we know cisplatin combines with the DNA of the cancer cell and inhibits the cell replication or cell division. The reason why, if you ask me why this combines with the DNA, not why cisplatin. Once I think somebody asked me the question in the theory class, why the cisplatin, not the transferrin, but the reason is not necessary for you all to know. But remember, DNA has nitrogen-containing bases, right? You have pyrimidine bases and purine bases. They're all nitrogen-containing bases: adenine, thymine, guanine, cytosine, right? So you know about the complementary base pairing. So what happens is that the nitrogen-containing bases, the bases get substituted with this molecule. But this also contains nitrogen. Can you see? The nitrogen, the base, gets substituted with these groups. In that situation, when this attaches to DNA, what happens? The cell replication or DNA replication will stop. So how this and why this cisplatin acting as an anti-cancer drug is because the cisplatin attaches itself to the DNA strand and prevents the cell division. So attacking the DNA strand, 1 mark, and preventing the cell division is 2nd mark. Suggest the geometry of the platinum center in the carboplatin complex This is clearly shown is square plane. Just why carboplatin does not show cis-trans isomerism? Because of the cyclic form. Cyclic form, it cannot, it cannot form the trans form. How can it form the trans form? Because you can see you can't have two oxygens like this on the opposite side. So this is this cyclic nature of the cyclic part prevents the formation of the trans isomer. I hope that's sufficient for the answer. 1 mark, right? Yes. The cyclic part of the bidentate ligand the cyclic part of the bidentate ligand does not enable the formation of the trans isomer. Does not enable the formation of the trans isomer. As for Chem 22, your answer is wrong because you cannot talk about the optical isomers here because it says cis-trans only. Right? There's not so cis-trans. There's nothing to do with superimposable mirror image and cis-trans, right? Superimposable mirror image is for optical isomer. This is only about, if it says stereo isomer, your answer is correct. If it is stereo, your answer is correct. But this is cis-trans, specifically geometric cis-trans, not stereo. That answer is wrong. Got it? Specifically cis-trans. Read the question carefully. Tetraplatin is a neutral complex containing ligands given reduced oxidation state of platinum in tetraplatin. Let's analyze. Chlorine is -1, this is -1, this is -1, this is -1, this is neutral, this is neutral. It's 4 plus, right? 4 plus or +4 because these are neutral. Minus, 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 4 plus. 4 plus. The compound M is made from 1,3-dimethylbenzene in 2-step synthesis. This is side chain oxidation. Structure of L will be 2-carboxylic acid, side chain oxidation. Alkali, MnO4, followed by acid. This is side chain oxidation. Carboxyl. Then you add PCl5. This is L. State reagents and conditions for each step. Step 1, you add alkali KMnO4 followed by acid. Otherwise, you get NONA. You get the salt if you don't add the acid. So NaOH KMnO4, heat under reflux followed by acid. NaOH KMnO4, you can say alkaline KMnO4, heat under reflux. And second, you need to add acid to remove the Na, sodium. Step 2, anhydrous PCl5. You have to say anhydrous because it's condition. Anhydrous PCl5. Write the equation for step 2. This is, let me write it here. This is C6H what? 1, 2, 3, 4. H4. There's 2 carbons here. C2, O2, Cl2. Right, so we can say C6H4, C2, O2, Cl2 plus, this is the product, reactant, C4, H8O4, PCl5, PCl5, POCl3, and HCl are the byproducts. This is Cl2, so there'll be, I think, 2 here. Balance the equation. 6, 7, 8, 9, 10. 10, yes. Put 2. Yes, of course, benzene derivatives always you heat under reflux because they're volatile. Reflux is better. Sometimes they give marks for heating as well. So remember, it's 2 PCl5, 2 PClO3, and 2 HCl. Because for 1 OH is 1 PCl5. So 2 OH, 2 PCl5s, right? And POCl3 and 2 HCl, the byproducts. So don't investigate a possible synthesis of M directly from benzene using COCl2 in the presence of AlCl3 catalyst. Okay, reaction 1, reaction 2. Reaction 2 is electrophilic substitution. Benzene suggests a mechanism for reaction 2. So this is a normal mechanism of Friedel-Crafts acylation mechanism. This is Cl. Normal Friedel-Crafts acylation mechanism. Cl, this is adjacent to adjacent hydrogen, and then this breaks in and forms the product. Normal Friedel-Crafts acylation. H plus will be given off. This is adjacent to adjacent. This circle, adjacent to adjacent. That's question 12-mark question. Please mark the answers and add the total. Right, so I think I should be able to do. We'll start on this as well. Any questions there? Okay, right. Okay, what I'll do is I will take a break now. As I mentioned, we'll take a break and then we'll continue the rest after the break.
Only person in this conference.
Let's continue. I hope everyone is back. Is the sound clear? Right. Fumaric acid is occurring carboxylic acid. Identify the products of the reaction between fumaric acid and excess hot concentrated acidified permanganate. This is the oxidative cleavage reaction. What happens is that this carbon-carbon double bond breaks, and you get this product, a dicarboxylic acid. In fact, one of the carboxylic groups is already present, and on the other end, it's an aldehyde which is produced because there's a hydrogen here and here. So the aldehyde is further oxidized to form the carboxylic acid. So the products of this reaction is 2 molecules of C2H2O4, oxalic acid. Oxalic acid. Fumaric acid can form addition and condensation polymers. Draw the repeating unit of the addition polymer of the polyfumaric acid. Simply break the pi bond, extend, put a square bracket. You have the hydrogen, carboxylic on one end, the carboxylic on the other end. You can put the carboxylic on the same side, doesn't matter. I mean, the same direction on the same carbon, but it can be both on top, doesn't matter. But generally, because of steric hindrance, one will be on the top and one will be at the bottom. This is a repeating unit of the addition polymer polyfumaric acid. Draw the repeat unit of the polyester formed when fumaric acid reacts with ethane 1,2-diol. So repeating unit, this fumaric acid part is a condensation polymer. So you have the OH is removed from one end, the alcohol end, the oxygen is removed. Carboxylic end, the OH is removed. The alcohol end, the H is removed, right? So here what happens, the previous one, to repeat again, you break the pi bond, extend, put a square bracket, that becomes the repeating unit, right? Simply break open the pi bond. And here you have the fumaric acid molecule, 2 carboxylic group, of course 2 hydrogens are missing here. And then the carboxylic end will react with the hydrogen of the OH to form the ester linkage. So it's a polyester. It says the ester bond should be fully displayed, so I have fully displayed the ester linkage. Explain why polyesters normally biodegrade more easily than or more readily than polyalkenes. The reason is that the ester linkage can be easily hydrolyzed by the presence of acid or alkali, whereas the polyalkenes, the carbon-carbon bond is quite strong, and they're non-polar molecule. The bond is quite strong and non-polar molecule, so therefore it is inert non-polar molecule. That's polyalkane. So polyesters, the ester linkage can be hydrolyzed by presence of acid or alkali, whereas the carbon-carbon bond is inert non-polar. I'm sorry, I just noticed it says repeat A part. What I did here was I just broke the carbon-carbon double bond here. When the carbon-carbon double bond is broken, you get this, right, from one end, and the other end, you get this, right? So this can be further oxidized. There are 2 molecules of oxalic acid produced. Clear? Continue to. No? This is oxidative cleavage. Remember oxidative cleavage reaction? If you have this group, you get a ketone. You have this group, you get carboxylic acid, RCOH. You have 2 hydrogens, you get carbon dioxide. You remember that oxidative cleavage reaction? No, okay. So this, you break this. This is if I'm to draw this molecule, you have to revise your A's, because A2 papers are synoptic. Without your A's, you can't go for the A2. This is a molecule I'm drawing now, detail. So I'm breaking this and adding oxygen here, oxygen here. So this is aldehyde part, so that will be oxidized to carboxylic. Fumaric acid reacts with cold dilute acidified permanganate to form compound P. Yeah. Diol, you can see a diol, 2 OH groups added, right? Diol. Only 3 stereoisomers of P exist. One of the stereoisomers is shown. You can see here the carboxylic acids are on the plane of the board, and the OH groups are coming out of the plane of the board, and the H are going inside the plane of the board, right? So now to draw the isomers of this, what we can do is we can make sure that now this is the 2 OH groups are going right. Both are coming out, right? So we can draw as one coming out, one going in. OH, one coming out, one going in. Right? This is one isomer. And then you can change the carboxylic position. The two carboxylic acids are on the plane of the board. I can make one carboxylic to come out or go in. I can draw one carboxylic to come out or go in. Right? Two isomers. Actually, there are three isomers. So here, the third one. Right? So depends on the groups. Now, see, this is both the OH groups are coming out. So you can't draw both as going in. That is wrong. That means if you draw like this, you draw OH here, both going in, that is wrong. Because you had just turned the whole molecule 380 degrees. Let's turn the molecule other way around. What comes out goes in. That doesn't make an isomer. That does not make it an isomer. So if both are coming out, the next one should come out, the one should go in. And here both carboxylic are on the plane of the board. So you can draw one as coming out or going in. Right? Clear? You can put the carboxylic here also at this position. There's no harm in that. Got it? Any questions there? There's a question I drew in the right from the top HOH. I don't know what you mean. Can you just show me, please? Or draw on the board. Then the carboxylic comes here. That's correct. That's correct. That's what I said. That's correct. It can either go, come. That's what I said just now. This can go in or it can come out over here. All right, so both correct. The enzyme fumarate catalyzes the reaction of fumarate ions with water to form malate ions. Describe with the aid of suitable label diagram how an enzyme such as fumarase can catalyze a reaction. This question we have handled so many times. Right? You can draw the block and key model. This is the enzyme, and the substrate which has the same shape of the enzyme get adsorbed to the active site. This type of questions we have handled many. This is the active site of the enzyme, and this is substrate. And we call this as getting adsorbed, not absorbed, adsorbed. That means get attached to the surface of the enzyme. The enzyme doesn't absorb, or the substrate get adsorbed to the enzyme. We say sponge absorbs water, but water get adsorbed to the sponge. It's the same thing, but depends on with respect to what species you speak to. Adsorption happens on the surface of the catalyst. So here what happens, you have, say, AB, and the bonds get weakened here. This is enzyme substrate, and then the product gets desorbed. Nothing happens to the enzyme. You get the products A and B desorbed. This is desorb. So first you draw this and then explain. I have done similar questions many times before. This is enzyme substrate. This is lock and key model. Specific substrate molecule. Specific enzyme catalyzes a specific substrate molecule reaction. The enzyme substrate complex, and this is enzyme, and this is a product. Any questions? You can write the explanation. The substrate molecule get adsorbed substrate molecule get adsorbed to the active site of the enzyme. Where the enzyme breaks the bonds between the reactants, break the bonds of the substrate. The enzyme breaks the bond of the substrate. And the product molecule get desorbed. The product molecule get desorbed. Desorb meaning leaving the catalyst. Got it? It's not a must to mention adsorb and desorb. Those are unique terms used for describing the catalytic activity. So I always like to use it, right? But that is always better to use it, I would say, because that's specifically used for explaining the catalytic activity. Got it? Not that you're going to lose marks just because you don't use those terms. Still get marks. The next one. Proline. It's a naturally occurring amino acid. Proline is often I'm sorry, just noticed your question. Can I also mention hydrogen bonds break? No, we don't know what bonds are there in it. The hydrogen bonds. Is there hydrogen bonds here? The hydrogen bonds, yes, you can mention. Otherwise, no need. Not necessary anyway, even if there's hydrogen bonds. Proline is often found bonded to glycine in a protein. Draw dipeptide pro-gly. Glycine, you can check the data booklet, the simplest amino acid, which has two hydrogens attached to the carbon. So here, this is what? This is the proline. Okay. So glycine, dipeptide, just two peptides. So you can draw the same molecule, proline here. And show the glycine, the amide linkage like this. This is a dipeptide. This is the peptide link. The peptide is specifically used for the protein polymer. Peptide link. Dipeptide means two monomers, two amino acids, but one peptide linkage. Even though it says di, but the peptide linkage will be one. You can also combine with this NH. You have a choice here. You can combine, if you're combining NH, then the carboxylic part will be as it is, but the NH, the other carboxylic group of the glycine, will attach to this NH. It's cyclic. This is cyclic, like CH cyclic. Proline is cyclic amino acid. Proline is one of the cyclic amino acids. It's an amino acid. It's a cyclic one. It's cyclic still. Name the type of reaction that forms a dipeptide to form 2 amino acids. This is a condensation reaction. You're also allowed to say addition, elimination, because you know this is addition followed by elimination, which is in short referred to as condensation reaction. So you're allowed to say condensation or addition, elimination reaction. Not just elimination, not just addition, that's wrong. You can say either condensation or addition followed by elimination, or simply say addition, elimination. Proline is able to form polyproline peptide chain. The section of the polyproline chain. So this is a primary chain. Amino acids are linked via amide peptide linkages, primary chain. Just why the secondary structures of polyproline cannot be stabilized by hydrogen bond. You can see it's very difficult to form hydrogen bonds because the primary structure get coiled. Beta plate structure will forming intra-hydrogen bonds, or alpha helix structure, which forms inter-hydrogen bonds. Those intra and inter-hydrogen bonds are quite difficult because this steric hindrance, because it's cyclic, bulky group attached to nitrogen. So the carbonate group can't easily form the hydrogen bonds because of this bulky cyclic nature, right? So you can mention due to the cyclic nature of the molecule, it cannot form inter and intra-hydrogen bonds. Inter and intra-hydrogen bonds due to steric hindrance. Cannot form inter and inter-hydrogen bonds due to steric hindrance because of the bulkiness of the molecule. Because of the bulkiness of the molecule. Sorry, previous one you want to see. I deleted it. Let me draw it in this itself. Before I move on to the next one, please let me know if I am to hold on. So I'm just going to draw it in here itself. Okay. A series of questions because electronegative oxygen can bond to carbon. I don't know about that. I don't know which question you're referring to. Can you show the previous? Yeah, this is the previous one. Now B. Okay. I hope this is clear. Which is B? There's no B here. A3. A3 because electronegative oxygen is bonded to carbon. No. Anyway, there's hydrogen bonds, right, between dipeptides. Anyway, any peptide has this carbonyl group and NH group, but it has still formed hydrogen bonds here. This is a hydrogen bond here. This is a hydrogen bond between peptide, not because of carbon is linked. That means there's no hydrogen bonds in primary amino acids. That means secondary will never form. That's not the case, right? But this is not possible because of this ring. You see, because of this ring, the bulky nature of the molecule will not enable to form hydrogen bond closely with the other molecule. So that is due to steric hindrance. I hope that's the answer. If I'm to write this, I will be writing that answer. But I cannot confirm it because the marking scheme is not out yet. But that should be the answer, right? Anyway, I can't confirm it until I see the marking scheme. This is the nature of the Cambridge paper. As I always say, you will never be able to get 100 out of 100 for the paper, right? But you can get the world prize, you can get the island prize, you can get the highest, but you will never be able to get 100. Even if you give the paper to me, I will not be able to score 100. I will not. I will say it boldly, right? Because I will not be able to score 100 out of 100 for any paper 4, because there'll be some point in the marking scheme, it'll be slightly a bit tricky. So don't worry about that. You can get 99, you can get 98, you can get the world prize, you can get the island top prize, you can get all those. But for the last 16 years of my teaching, I never seen anyone getting 100 out of 100 for Cambridge. But many of my students, I got 600 out of 600 for Edexcel. That's possible, but for some reason, I cannot get 100 out of 100 for Cambridge because there is some now. For example, this particular question, such example. Now there can be so many answers. Now it depends on which point of view you look into, because that doesn't mean that the answer is wrong. Sometimes that answer may not carry in the marking scheme, because chemistry is such a vast subject, because some particular concept can be explained in so many different ways. For example, if I ask a question, I can't. One person can explain. Say, answer is A, B for the question. There are three answers: A, B, C. So one say, okay, this is the answer A. Answer B is also can be answer, but C can be wrong. But that means there will be two different explanations. But one, the person who made the question, he will strictly believe only on answer A. Sometimes he had never heard about answer B in his life. Sometimes he will not accept the answer B. So that's the reason why, even for us, until marking scheme is given, we can't say for sure. But this is, if I am to write, this is what I write about steric hindrance, which is should be accepted, right? Got it? Nothing else I can think of as to my understanding. Only way to check is that after a few months when the marking scheme is out. But this is only definitely the steric hindrance. Got it? Any questions further? I hope it's clear. Okay. The reaction scheme shows several reactions of proline. This is A, Q, this is this. Okay, fine. Got an equation for the reaction of proline with NaOH. This is what happens here is just ONA. The same structure, carboxylic end. Turns out to be ONA. So the equation, we have to count the number of carbons and hydrogens and write. This is CH2 here, CH2, CH2, the carbon CH here, carbon here. So count the carbons, 1, 2, 3, 4, 5. Nitrogens, hydrogen and nitrogen 1. Oxygen 2, count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so the product, C5H9, NO2Na. Oh, where did I put O2? Yes, okay, fine. This is NaOH. And the byproduct is hydrogen. Right, just hydrogen is given now. Oh, it's already given, I'm sorry. This equation is already given, so it's easy. I thought it's not given. So NaOH, C4H7, they separated the carbons, NHCOONA plus half H2. H2O, I'm sorry, not H2. H2O. It will be H2O. A reaction with what? Sodium will give you hydrogen, or the sodium hydroxide, it will be water because acid-alkali reaction. So that will be half H2O, right? Yeah. These questions, we draw the benzene ring instead of counting it. It is wrong. Yes. When you write the equation, in the molecular formula form, not in displayed formula form. It's already given as molecular formula here. Proline has a secondary amine functional group. Secondary amines react with acyl chlorides. For example, dimethyl reacts with is acid chloride according to the following equation. This is addition followed by elimination. It's a condensation reaction. Yeah. That suggests the skeletal structure of R, product of reaction 2. Okay. Let me draw it here itself. This acid chloride will react with both amine and the carboxylic end. skeletal structure. So you have, will it react with the carboxylic end? No, it will not react with the carboxylic end because only the amine end, right? Because carboxylic end, there's no reaction of carboxylic. We react with the alcohol, not acid chloride. So this will react with the amide to form the amide. Right, this is the molecule. Amide link is formed. This is the answer. Clear? Or just the reagent required for reaction 3. Reaction 3 to reduce the carbonyl group to a CH2, that is lithium, aluminium hydride in dry ether. Lithium tetrahydroaluminate or lithium aluminium hydride. Reduction of any carbonyl group, aldehyde, ketone, carboxylic acids, esters, amides can be reduced by lithium aluminium hydride, but sodium borohydrate can be specifically used only for reduction of aldehydes and ketones. Proline was first synthesized in the laboratory using multi-stage synthetic route. What's happened here? Single product here. See what has happened here. The pi bond is broken. You can see this molecule over here, and these two of these molecules. Right, this is COCH2, two of it. Anyway, so this is, I don't know exactly what has happened here, but the pi bond is open, and pi bond has opened, and then it has attacked this molecule, this carbon over here. This is what I can think of. Yes, this is there, this is there, and this one of the hydrogens. This is as it is, this whole thing. Yeah, let's see what the question. Name all the functional group present in reactors in stage 1. You have the ester functional group here. You have the nitrile functional group here, and carbon-carbon double bond functional group. So you have the ester, nitrile, CC double bond. Just a type of reaction that occurs in stage 1. Stage 1 has to be addition, right? It has to be addition reaction. Because two reactants react to form one product. Two reactants react to one product, which has to be addition. Got it? Electrophilic addition, yes. Yeah, it's much better. Electrophilic addition. Electrophilic addition, yes, because a carbon-carbon double bond molecule. Stage 2, U reacts with V to form W. U reacts with V to form W. Let's see what is this V, reagent V. This has to be lithium aluminium hydride, or even hydrogen nickel catalyst will work. This is reduction of cyanide to the primary amine. Add 2 hydrogens to this carbon and 2 hydrogens to this nitrogen. Lithium aluminium hydride is suitable in dry ether conditions, or hydrogen nickel catalyst also can be used. There's a carbon-carbon triple bond there, carbon-nitrogen triple bond. There's a question, I need a small clarification when it's nucleophilic addition. nucleophilic addition. Yeah. Charge on the nucleophile, is it positive? Nucleophile is nucleus-loving species. Nucleophile is a nucleus-loving species. So how can a positively charged species can be a nucleophile? Can it be a nucleophile? Can this like a nucleus? The question itself is invalid because nucleophile cannot be positive. Nucleophile can be either neutral, like water, for example, or ammonia, or it can be negatively charged, like hydroxide. But nucleophile cannot be positive. Got it? Nucleus, phile, liking, loving. Nucleus loving species. Electrophile, then electrophile is electron loving. It can be positively charged, it can be even neutral. Like for example, bromine, addition of bromine to alkene. Bromine is neutral, right? It can never be. How can electrophile be negative? Electrophile is what? Electron loving species. So if this is electron, can this like the electron? Can this attract? Electrophile can never be negative. These are all A's. Revise the A is organic. Clear? Anyway, that's good that all is you clarified, but I further advise you to revise the organic chemistry of the A's. Which question we did, I forgot. Reagent for this is the question. Yes, lithium aluminium hydride or nickel hydrogen. Nickel can be used. Stage 3 takes place in presence of acid catalyst. X and Y are the only products of the reaction. Suggest the type of reaction that occurs in stage 3. For 3, ethanolic ammonia? No, never. Ethanolic ammonia is what? You can't convert cyanide to CH2NH2 by ethanoic ammonia. Ethanoic ammonia, if you have a haloalkane, so that this discussion shows that your AS is gone, right? You have to revise a lot on AS. Ethanoic ammonia is conversion of, anyway, it's good to know before the exam that you need to revise. This is to convert haloalkanes to amine. You will find the instant notebook very handy, so you can at least go through that. You know the reactions then. This conversion of the cyanide to amine, lithium aluminium hydride. So this is a different, completely different reaction. This is haloalkanes to amine. There's no haloalkane here. Number of carbons the same. 3 carbons. 3 carbons. Here you're increasing number of carbon atoms here, right? I mean here the number of carbons is a different reaction. Amine, haloalkanes to amine. Okay, now what has happened here? Type of reaction that occurs in stage 3. Analyze carefully what has happened. Look carefully. Look at this. We have CO2C2H5. You can see that here clearly here. CO2C2H5. And let me label this 1, 2, 3, 4th carbon has the amine. 1, 2, 3, 4th carbon has the amine, correct? This has, something has happened and this has attacked this one and formed the amide link. It has formed a cyclic compound. And this fellow has gone off. It's a very strange reaction. Yeah, this is what has happened here is that I'm quite sure this is hydrolysis that taken place. So the alcohol C2H5OH is removed and the carboxylic acid, first is hydrolysis, that's right. First is hydrolysis and then the condensation is also has taken place. Not just hydrolysis, because hydrolysis of W will give you CO2H. That's not the product S, product X. The main type of reaction which has happened here is condensation. Condensation, right? Because addition followed by elimination. This is condensation. Hydrolysis, of course, first has to happen, but the final reaction is condensation. Initially, hydrolysis has taken place. C2H5OH is alcohol, which is Y. And then the carboxylic acid, this NH2, forms a bond with this carbon to form the amide link, and it forms a cyclic compound. It's easy to identify if you label this, and the fourth carbon has the amine. Clear? Can we say hydrolysis then condensation? Because this is the type of reaction. They're asking for one type. Not exact, but condensation is for sure. But just writing hydrolysis, I'm quite sure that you will not get marks. Hydrolysis alone, you will not get marks, as per my understanding. But depending on the marking scheme, because if majority happen to write hydrolysis, they will give marks for hydrolysis. That doesn't mean that's the answer, right? If that is how the marking scheme works. So if the actually it's hydrolysis followed by condensation. So the main reaction here is condensation, even though the condensation occurs after hydrolysis. So if you write in both hydrolysis and condensation, then definitely you will get the marks because your condensation answer is correct. And the hydrolysis answer is not wrong. But if you write hydrolysis alone, it's not correct. You understand what I mean? Whenever you write two answers, remember, this is the principle. When you have two answers, if one answer is wrong, the other answer is right, then your answer is wrong. Because, say, for example, answer is A and B you wrote. A is wrong, B is right. So you're not expecting you to get any marks because you've written the correct answer and the wrong answer. That means you're examining, in other words, you're examining the examiner. You're telling him to select the correct answer and mark it for you, right? So you can't write multiple answers. But in this case, if you write hydrolysis at condensation, still you get marks because hydrolysis is not 100% wrong. It's the first step what happens, right? Question, when condensation occurs, it breaks a carbonyl bond, right? So alcohol anyway is removed. No, here there is no condensation. Actually, first step would be the hydrolysis, right? Because there is no reactions of esters. This is an ester link. You get the ester here. Ester cannot be forming an amide link, right? So first is the hydrolysis should take place, and then you get the ring. This attacking the carbon, forming the ring. Clear? I hope that's clear. Yes, tell me. Any questions? No, it's not that. Even if you write hydrolysis followed by condensation, it's okay, but just writing condensation is quite enough because it says the type. So we can't write two types. It has to be one answer. So if you just write condensation, fine. After several further stages, Z is produced. What's the difference here? What's the difference? Anyway, we'll see. In the final stage of the synthesis, Z reacts via nucleophilic substitution mechanism to form proline. Yes, that is, you can eliminate. Repeat the diagram to describe. Now see, this is nucleophilic substitution. Not quite sure this is SN1 or SN2, no idea. secondary carbocation. This is secondary carbocation here. We'll see. Can be SN1 or SN2. Complete the diagram to describe the reaction mechanism of the final stage. Draw curly arrows, ions and charges, partial charges, and lone pairs of electrons as appropriate. Draw the structure of any organic intermediate ion. Yeah, you got the point here. The answer is here. Answer is there. Intermediate. What is intermediate? Which mechanism forms intermediate? SN1. Now, because of this point, we know it is SN1 because it says intermediate. That means this. You have, this is plus delta, minus delta. You break the carbon-chlorine bond heterologically. NH2, CO2H, positive charge. This is the intermediate. It says draw curly arrows. I have drawn the curly arrow. Ions, charges, show, and the lone pairs of electrons. The lone pairs of electron. Now this will attack this and form this proline. Can you see? This is a bond which is formed with this carbon because this carboxylic group is a side chain here. So therefore, this NH2 should attack to this carbon over here. Got it? And so this is a nucleophilic substitution, and we know that it is substitution. So that means chlorine should get substituted. The question arises whether it's primary or secondary because the secondary halide alkane. And because of this intermediate, because SN2 doesn't have intermediates, it only have a transition state, right? So that from that we know it's SN1, unimolecular nucleophilic substitution reaction. And then this attacks here, and this forms the ring. Identify with an asterisk the chiral center. Only one chiral center. 4 different groups attached. There's a hydrogen here, which is not shown. Let's get it to a formula. Part of the structure of the gelatin is shown. Identify the number of amino acids. The best thing you can do is break the molecule at the point of the amide link. Break from the amide link. Break from the amide link. All the molecules. Let's see, this is break from the amide link. Break from the amide link. Yeah. So identify the number of amino acid units. It doesn't say type of amino acids. How many are there? So remember, it is not the different types of amino acids. Remember, the question should be read carefully. Number of amino acids. It can be the same one, same type. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 amino acids. So there are some of them are same, but it doesn't say how many. Identify the different types of amino acids. It says just identify the number of amino acids, right? At pH 6.5, proline exists in aqueous solution as sweet ion of proline. The structure of proline now. I just draw it here itself. The structure of proline, sweet ion of proline. is that you have CO2 minus NH2 plus, and which has both positive and negative charges in the same molecule is referred to as zwitterion. Amino acids exist as zwitterions. The carboxylic end can deprotonate and form the anion, and NH2N takes H plus, or NHN takes H plus. Only the proline is a cyclic amino acid. This is a zwitterion. This was draw, and it says explain. So you can just explain. You can say the hydrogen of the carboxylic deprotonates and NH group protonates, or hydrogen of carboxylic deprotonates to the NH group. That is clear. Oh, this is how many questions more? Okay. It's the best paper I've ever seen. Such a long paper. Right. The isoelectronic point of amino acid is a pH at which it exists as zwitterion. Okay. At these pH, these amino acids, they exist as zwitterions at this pH. Only at this pH. That is why we maintain buffer solutions. So at this particular pH, they exist as zwitterions. 3 of the amino acids of gelatin, acids in gelatin are proline, cyclic, alanine, glutamic. And their isoelectric points are given. Isoelectric point is the pH of the amino acid, which that amino acid exists as zwitterion. That means if you have the buffer pH 6.5, this will be zwitterion. That means it will be CO2 minus NH2 plus, CO2 minus NH3 plus. Right? If you maintain the buffer pH at this particular pH, isoelectric pH. What's the isoelectric point? That is the pH at which that particular amino acid exists as zwitterion. A mixture of these amino acids was analyzed by electrophoresis using buffer solution at pH 4. Now see, buffer pH 4 means none of these will be at zwitterion, right? Because pH 4 is enough, it's not matching with any of this. So they are not existing as zwitterions in this buffer. So pH 4 means this proline will take H plus, because pH 4 is acidic. It will take H plus and form this ion. Even alanine will take H plus and form this ion. But glutamic acid, pH is 3.1, and the pH of the mixture is more than 3.1. That means this will act as relatively an alkali. Even though pH 4 is still acidic, but it will act as a relatively an alkali, right? So if the pH is greater than the isoelectric point, then it is considered as a basic. Therefore, this carboxylic ends, because it's not zwitterion anyway, will deprotonate and form negative charge. But in this case, where the pH is greater than the isoelectric point, so this is pH is less than isoelectric point. Can you see? pH is 4, less than isoelectric point. That means this solution is acting as an acid then. Therefore, NH2 gets protonated. If the pH is greater than the isoelectric point, it is considered to be basic. This solution is considered to be basic. That means it will deprotonate the oxygen. So, I mean, H plus. So you have positive charge, 2 minus charge. Now it's easy for you to understand the positions. 2 minus meaning it will, let's analyze the minus one first. You have it will move to cathode. These two will move towards the cathode, which is far further. This will move more distance, 6.0. This is, and alanine will move more distance. I'm trying to show alanine here. As for the proline, because a bulky molecule, less distance, even though both have same positive charge. This is proline. And the glutamic acid will travel the most distance. Even though it's bulky, it travels the most distance because charge is 2 minus. Charge is 2 minus. That will travel more than these two. So 4 marks, I'm sure you'll get about 2 marks for this drawing, relative directions and distance. You get 2 marks. Balance 2 marks is for the explanation. Clear? Let's write the answer. If you want, this is, I'll explain again. The theory here is the pH, if it's less than the isoelectric point, it is considered as acidic. That means pH 4 relative to 6.5 is acidic. Therefore, it will give H+. So this will be NH2+, NH3+. If the pH is greater than the isoelectric point, this is isoelectric point 3.1, pH is greater than that. In that case, we consider it will be as basic. That means it will deprotonate, remove the proton. So it's 2 minus here, remove the 2H+, plus. So 2 pluses will move towards negative, minus will move towards positive. 2 minus charge will travel the most distance compared to the 2 pluses. And the proline is bulky, less distance. Alanine is less bulky, more distance. Clear? Chem 3. Let's write then. Both proline and alanine will protonate H+ from the buffer solution. As a result, nitrogen will carry a positive charge. Whereas glutamic acid will deprotonate to hydrogen, whereas glutamic acid will deprotonate to H+. As the buffer pH as the buffer pH is less than, as the buffer pH is greater than isoelectric point, forming 2 minus. Hence, glutamic acid will travel towards the positive terminal. whereas both proline and alanine will travel towards the negative terminal. Proline travels less distance compared to alanine. Proline travels less distance compared to alanine. Due to its bulky cyclic chain. This is bulky cyclic structure. Due to its cyclic structure, you can say. Clear? The weak acid ACES is a compound that can be used to make buffer solution for electrophoresis experiments. The anion of the sodium salt of ACES, the strong base. Our solution is prepared by following steps. 3.5 grams of this sodium salt is dissolved in 100 cm³ of distilled water. 50 cm³ of 0.2 mole per decimeter cube dilute hydrochloric acid is added to the solution. The resulting mixture is transferred to 250 polymetric flask. That means this 250 is the volume which we need to consider when we are calculating the concentration, not this 100 or 50. The total everything is in 250 now. The salt reacting with the acid with 1:1 ratio. Now what happens here is that this is the acid. So sodium salt is what we take. You know, buffer solution is if you take acidic buffer, it's a weak acid. When it's mixed with the salt of that weak acid, it's a acidic buffer. So you have the salt of it. Where is the weak acid? When you add the hydrochloric, part of this salt will react with the hydrochloric. Why this salt reacting with hydrochloric? Because salt is what? A strong base. Since salt is a strong base, right? Salt of weak acids are bases. That's why it's reacting with hydrochloric acid, right? So what happens in the salt reacting with hydrochloric acid? It forms the acid again. Which acid? The weak acid. We don't have the weak acid here. We have the salt and the strong acid. Salt and strong acid will never give you the buffer, right? It should be the salt and weak acid. Now, similar questions I had done in my theory lesson. And this is an easy question, right? Because we had done enough of questions of this nature in the study pack 7.B, acid-base equilibrium. So here you have to find the moles of the salt, moles of the acid, and you subtract and get the value for the moles of the weak acid, because the salt reacting with the acid to form the weak acid. We got the moles of weak acid, we got the moles of the salt. 250 is the volume. You can find the concentration and you can find the pH. So the first step would be to find the moles of the salt. Moles of the salt. Mass is given as 3.5, molar mass is 204.1, it will be 0.017 moles. And you find the moles of acid, HCl, N equals Cv. It says the reaction, the ratio between the salt and the acid is 1:1. Then this amount of acid reacting with the same amount of salt, you can get the remaining salt. Remaining salt, 0.017 minus 0.01. Remaining salt will be 0.007 moles. And therefore, moles of weak acid is 0.01. How do you know that? Moles of hydrochloric is a moles of weak acid because acid reacting with the salt to form the weak acid again. So you got the remaining salt moles, remaining acid moles. You have to find the concentration now. Find the concentration of the salt. 0.007 in 250, number of moles in 1000. Find the concentration of weak acid. 0.01 is in 250, number of moles in 1000. Salt is 0.028 m. Acid is 0.04 m. That's it. You can use Ka equation. That is H plus Ka times acid over salt. Ka is not given, the pK is given, so you have to find the Ka. Do the separation, and separately you can calculate that. pK is minus log to the base 10 Ka, so therefore Ka is inverse log minus 6.88. Inverse log minus 6.88 is how much? 1.318 to the power minus 7. 32, yes, you can take as 32. And then you substitute that. H plus 1.318 into the power minus 7. Acid concentration is 0.04. Salt is 0.028. You get the H plus. What's H plus? H plus is 1.88 10 to the power minus 7. pH equals minus log to the base 10, 1.88 10 to the power minus 7. That's the answer. At least 2 decimal places. 6.73 is the pH. This is the easy question that I kept for the last. Anyway, compared to the others. This is how you find the pH, I mean the Ka from pK. First you got the moles of the salt, moles of the acid, and the acid reacting with the salt. Salt is in excess, acid is limited, so acid reacting with the salt, and there will be remaining acid here. When acid reacts with the salt, you get the weak acid. That will be the same as the moles of the HCl. So we got the moles of the remaining salt, moles of the remaining acid, weak acid, which is formed. You get the concentrations because all those moles are in 250. And then you get the Ka. This is the equation of the buffer pH. H plus equals Ka acid over salt. You can work out the H plus concentration, and then pH equals minus log to the base in H plus. So you get the pH. Moles of weak acid is a moles of HCl because ratio is 1:1. When salt reacts with HCl, it will form the weak acid. Weak acid and the sodium chloride. Get this weak acid. Instead of Na, you get SH here, right? And this NaCl. I got H plus ions. H plus I got from this equation. This is the equation which is used to find the pH of the buffer. You got the Ka. It's pK. From the pK, I got the Ka. Acid and salt concentrations I found. Then I got the H plus. Chem 16, is it clear? This is the equation for the buffer. You can also use pH equals pKa plus log salt over acid. That's also fine, but in that case, you'll be careful to use brackets properly. Otherwise, log. Some students don't use the brackets properly, so when you're handling log calculations, be careful. So that's why I usually don't use that. You can use that also, that equation pH equals pKa plus log salt over acid. So many don't put a bracket. So what happens then? how the calculator understands is that log salt concentration, the answer will be divided by the acid concentration. That is wrong. So you have to put a bracket over here. Log should be the ratio of this. Any questions here? And the total, right? And let me know the marks. You can message me, please. If you got low marks, don't worry. You're not going to get this paper. Don't worry. So be positive, think positive. At least try to identify your weak areas, right? Identify the weak areas, revise those sections. That's number one. That's the first thing you should do before the exam. Don't get disappointed. I got 40 marks, I got 50 marks, so I'm useless. I'm not going to do the exam well. No, you might get a very easy paper this time. You might get 40 for this, and you might get 95 for the real paper. Things happen like that, right? So don't get disappointed, right? I don't know. Yeah, we haven't done the February-March papers, right? So this paper is abnormally long, I would say. I'm extremely unhappy about this paper, right? It's so long, so long. It's usually, in February, other papers, we just finished by 2 hours, 2 or 15 minutes. Now, this took about nearly 3.5 hours to complete, right? So I am not happy with that anyway. That's not a problem. If that is the case, it's going to affect everyone, right? Not only you. If it is affecting me, how about others? It's affecting everyone. So it's not going to be a problem anyway. Threshold grading will go down in that case. So nothing to worry. Even myself, this is the longest class I had ever discussed a single paper, right? Anyway, it's very interesting and very, important paper, I would say. You can identify very important areas that you need to revise again. That's number one. And second thing we should do is, we have done about 5 to 6 years of papers now. Go through all the papers which we have discussed. This is an exercise which you should do at least 1 or 2 days before the exam. I said in the discussion that to mark the difficult questions during the discussion, you have all the questions marked, so you can just revise those questions. And I would advise you, if time permits, don't stress yourself. If time permits, do some more papers, right? Do some more papers. And if possible, the variants. I would advise this. So there are two options. Am I to do all the papers for next 10 years, or am I to do the variants of the recent papers? My answer for that question is, if you can do both, best, but I know the time is now about 1 week more for the exam. If you haven't done the old papers, don't worry now, because worrying will give you negative results. I think worrying will never give you extra 1 mark. It will give you -1 mark. So be happy, don't worry, right? So if you have not done the old papers, I would advise the best thing you can do is do the very recent papers, because history repeats. I have noticed to myself, they take questions from the variants of the recent papers. Right? You can notice some years, 2 years, paper 4.3 question is in paper 4.2 on the next year. Same question. Right? Great. Some students have got 90s. Very happy about that. Chem 394. So you can just type your answers that you have marks. Not to compare anyone, but each one is unique. If you can just tell me your marks, I'll be a little happy to see. I hope everyone has got above. Even if you got 70, it's okay. Of course, all of you should and will get it. I hope, because we have done enough papers. Got 90, that's great. That's great, right? Average-wise, this is a quite difficult paper, I understand. If you can get 80 for this paper, I'm quite sure that you will do very well at the exam. Even 70 is okay. Even if you got low marks, it's okay. It's not the same question, it's not going to repeat. So this is my advice. Go through your theory, rapidly go through your AS work, past papers, and do the recent papers with the variants. Right? So I wish you all the best for the exam. I will not be doing any more classes for paper 4. And I think we have a few I think paper 5s to complete, maybe 1 or 2 paper 5s. I didn't still receive the February, March paper 5 still. This was given to me by one of the students in the class. So I don't know. I tried to find it online. It's not available anywhere. Either the marking scheme is released at this point of discussion. Anyway, so let me know whether if you need to have a class next Saturday. I think we will discuss one more paper 5.2. Paper 5.2 exam is I think on the. Let me check. On the 10th of May. Photo is on the 4th, right?